We're surrounded by numbers every single day. Averages, stats, scores. But what happens when those numbers don't tell the truth? When just one single rogue number can throw off the entire story?
Okay, so picture this. You're watching a figure skating competition. The judges' scores are popping up, and everything looks pretty consistent, right? We've got an 8.1, an 8.3, a really solid 9.1, and even a 9.9. It's looking like a fantastic performance.
And then, bam, a 6.0. Whoa, that one just sticks out, doesn't it? It feels like it wandered in from a completely different event. It just doesn't fit.
So this brings up a really big question. If we just do a simple average, that one super low score is going to drag the whole result way, way down. Is that really fair? How do we figure out what the real score should be?
Well, that one low score has a name. Statisticians call it an outlier. It's basically an extreme value that's just hanging out way far away from the rest of the group. And as we just saw, a single outlier can totally warp the average and give us a picture that's, well, just plain wrong.
Now, a weird figure skating score is one thing, but this whole problem of bad data, especially outliers, has absolutely massive consequences in the real world. We're not just talking about little mistakes here and there. We are talking about a multi-trillion-dollar problem.
Yep, you heard me right. According to an estimate from IBM, poor data quality costs the U.S. economy something like $3.1 trillion every single year. It's just a mind-boggling number that really shows you how critical it is to have clean, accurate data.
So, how does a number get that big? Well, think of it like a chain reaction. Bad data leads to bad decisions. Imagine a company basing its entire inventory plan on an average sales number that got skewed by one store having a massive once-in-a-lifetime sale. Suddenly, they've got way too much product everywhere else. That's how you end up wasting marketing dollars, frustrating customers, and running into all the serious problems you see here.
So if we want to dodge these huge, expensive mistakes, we have to become data detectives. And what's the first thing any good detective does? They identify the culprits. In our world, that means spotting the problems that can send our whole analysis off the rails.
And there are usually two main types of troublemakers we're looking for. We've already met the outliers. Those are the extreme weirdo values. The other big one is missing values. That's just what it sounds like. Gaps in our data where information that should be there just isn't. Both of these can cause some serious headaches.
Let's focus on how to spot those outliers. Sometimes they're just simple typos. Somebody meant to type a 9 and typed 99 instead. Other times they're real but super rare events. A fantastic tool for finding them is a box plot. The main box shows you where most of your data is clustered. And those lines sticking out, the fences, show the expected range. Any dot that falls outside those fences, boom, that's a potential outlier you need to investigate.
Now, our detective work isn't just about the data that's there that's weird. It's also about what's not there. Sometimes data's missing for totally random reasons. Maybe a survey participant just skipped a question, or a piece of lab equipment had a glitch. It's a different kind of problem. But for now, let's get back to what we do with those outliers we did find. Okay, so our detective work paid off. We found the outliers. Now what? This is the big question. What do we do with them? Do we just get rid of them, or do we try to fix them somehow? We've got two main strategies here. The first is called trimming. This one's pretty straightforward. You just chop off the highest and lowest values and throw them out. The second method is a bit more subtle. It's called winsorizing. Instead of tossing the outliers, you replace them with the next closest number. You're basically capping them so they can't have such a huge influence. Let's go back to our skater to see how trimming works. First, you line up all the scores in order. Then, you decide to trim the lowest and the highest ones. So goodbye 6.0 and see you later 9.9. Then you just average what's left in the middle. The new trimmed mean is 8.50, which feels a lot more fair, doesn't it? And this is exactly why winsorizing is so useful. When you trim, you're actually losing data, which can be a big problem if you don't have a lot of it to begin with. But winsorizing cleverly lets you keep all your data points. It just dials back the influence of the extreme ones. Pretty smart, right? So these techniques, trimming and winsorizing, they're not just one-off tricks. They're part of a whole family of methods. Think of it like a data detective's toolkit, full of specialized gadgets to help you get a clear picture, even when the data is messy.
The official name for this is robust statistics. And really, the name says it all. The whole point is to create methods that are tough, that are resilient, that won't fall apart the second they run into a weird outlier. They're designed to be, well, robust.
against the messiness of real-world data.
This little table here is a perfect cheat sheet for our toolkit. The regular old mean, it's super sensitive, great for perfect data, but not much else. The median, which is just the number smack in the middle, is really robust, great for when you've got outliers. And the trimmed mean, like we saw, is also robust and perfect when you know you've got some extreme values to deal with.
And this isn't just theory, you guys. These robust methods are used everywhere. They're in Olympic scoring to make sure one biased judge can't tank an athlete's score. Economists even use them to calculate inflation, trimming out super volatile prices like gas and food to get a more stable, realistic picture of the economy.
So if you take one thing away from this, let it be this. A single number, especially an average, almost never tells the whole story. The real story is often hiding in the details, in how the data is spread out, and in the choices somebody made about how to handle those pesky outliers. So I'll leave you with a final thought. The next time you see a news story about an average salary or an average price, will you stop and think for a second? Will you put on your data detective hat and ask yourself, I wonder which outliers they left in? Or maybe even more importantly, which ones they took out?